Okay, welcome everybody to today's installment of the California Dreams Technical Seminar Series. We are very happy to have with us today Umesh Mishra. Umesh, I think, is our first active dean to be presenting to our series, so we are excited about that. Umesh has more good things that I could say about him than we have time for, but he has extensive experience in academia and in industry, including about 10 companies that have spun out of his group, including one of the more recent ones, Transphorm, which was just acquired by Renesas in 2024. So we're very excited about that. Umesh is a fellow of the IEEE, and he has had 81 Ph.D. Students that have finished under his supervision, 15 of them women, and 11 of those graduates are faculty members in prestigious universities, including 5 of them being women. So I wanted to highlight that in a time when we are emphasizing the importance of bringing more people into the microelectronics field. So with that, I will turn it over to Umesh.
Well, thank you very much, Steve, for those kind words. Can you hear me now?
Yep, okay. Sounds great.
Yeah, and so what I'm going to talk about today is the history of gallium nitride electronics and the emergence of nitrogen polar GaN. I'm happy that Steve is in the audience. He and I have been partners in crime for a long time, and I hope you enjoyed the presentation. Let me just see now. I have to just, okay. So why is GaN the next preferred generation technology alongside silicon? And the reason we believe, I definitely believe this, is that semiconductor technology has to be high performance based on application, of course. It has to be very reliable. It has to have a roadmap for lower cost with every generation. And low cost is not magical. It actually requires very wide market penetration. So gallium nitride, more than any other semiconductor, satisfies all these requirements. Photonics applications, LED and lasers, work done here at UCSB by Shuji, Steve, and also now recently Jim. And then electronic applications, wireless base stations, radar, these are large, big applications. Sensing applications, sensing and transmit in the UV, and so on and so forth. So gallium nitride as a material system is not just a one-string band. It basically is a full orchestra. So GaN is, why is GaN so remarkable? It's a direct bandgap material. It emits light from a dislocated material. This is very unusual. No other semiconductor puts out light from a dislocated material. Nobody would have thought that it would be part of a $10 billion, $30 billion now industry. And GaN is a wide bandgap solution. When we started doing GaN, we basically had to fight this myth that silicon carbide was better than GaN because it had a dislocation-free substrate, and we had to say that it really didn't matter, and it didn't. And then, of course, it has, it's a tight lattice, and there's no shear stress in GaN, which basically allows the GaN dislocations to be rigid. They don't move. And that's a big deal because in other material systems like silicon carbide, the dislocations are actually free to move because of the large lattice constant. There are broad-based applications of GaN. I've said this before, so that's why we call it a future-proof semiconductor. Solid-state lighting, airborne radar, data center power supplies. This is becoming extremely important today because of AI. Compact chargers, the stuff you buy in Best Buy or wherever, has got GaN inside now. Displays, 5G base stations are all GaN now. All the new rollouts they're all GaN based. And then home energy systems where basically you have battery storage of, say, solar or something. These are slowly moving over to GaN for basically power conversion applications. And electric vehicles, of course, this is right now, is dominated at the moment by silicon carbide and silicon, but GaN is starting to make inroads into this, and you'll see in the next 3-4 years, GaN is going to start becoming very important in EVs as well. So if you look at power electronics, this is an RF talk, but I just want to give a background. If you look at power electronics, the GaN, I've borrowed this from Transphorm, so forget it's not meant to be propaganda, it's meant to be. It basically show you the landscape of basically low voltage GaN. Low voltage GaN is the stuff that will go onto the motherboard to go to point of load applications, 48 volts to 1 volt, for example. That's where low voltage GaN will play. 650 volt GaN is a big market for power. 1200 volts is for where you have a 480 volt grid, for example. And then there are trains and so on and so forth, where GaN, I don't think, will play, but that's a smaller part of the market. And people talk about GaN versus silicon carbide. This has been my life, unfortunately. I have nothing against silicon carbide, but every time we talk about GaN, we have to talk about why not silicon carbide. And basically, and the fundamental advantage of GaN has been and will always be physics. The electron in GaN has higher mobility than the electron in silicon carbide, and the band gap is similar. And therefore, as my ex-advisor, Professor Eastman, used to say, the only thing God gives you without asking you for a tax, I'm paraphrasing, is electron mobility. So never give up electron mobility for anything. I believe he was right, and that's my guiding light. You can see also that gallium nitride and silicon carbide perform very similarly today at GaN being slightly better than silicon carbide. This is a power conversion application where you're trying to convert about 10 kilowatts of power, and you can see GaN performs very well relative to silicon carbide. GaN can also be a 1200 volt device. We're going to talk about devices more like 20, 30 volts in the talk going forward, but I just wanted to let you know that GaN-on-Sapphire can also be a 1200 volt device where it performs against silicon carbide extremely well. So it's, again, a broad brush, very useful materials and device technology. And therefore, I hope I've convinced you that because of this huge photonics applications, huge power electronics application, our RF applications ride on they're basically in the wake of these other applications. So we can actually benefit from the economies of scale that the others provide. And just so that we know that the adoption of LEDs in lighting marks one of the fastest technology shifts in human history. The source is IHS. So the reason is, once something like this hits, nothing scales in life like a semiconductor. And this was the biggest, one of the greatest transitions that have happened in our lifetime. That's for background. Now let's look at going forward, right? Gallium nitride, it comes in two flavors, gallium polar GaN and nitrogen polar GaN. And I'm only going to be talking about lateral gallium nitride, not vertical gallium nitride, which is also a field unto itself. So gallium nitride and AlGaN, this material system is much akin to a MOSFET. And by that, I mean, if you look at AlGaN, think of that as silicon dioxide. GaN, think of it as silicon. And then you have a source, drain, and gate. So it's effectively a MOSFET on steroids, okay? And what are the steroids that it's on? It has this dashed line is a two-dimensional electron gas. The mobility of this two-dimensional electron gas is 2000 in gallium nitride. The two-dimensional electron gas in silicon the mobility is 50. So the only way silicon can actually be a competitive semiconductor relative to GaN in any way, shape, form is when it is highly scaled. That means it's a 28 nanometer process, something like this, okay? But it also has to be self-aligned. So when silicon tries to do RF, it can. The reason is at 28 nanometers, it's a ballistic transport, so mobility doesn't matter. However, when you're that scaled, you have no breakdown capabilities. So silicon can perform, but it'll produce very few milliwatts per device, which then has to be taken care of by having multiple devices, which gives you the watts, and then the antenna gain of the multiple devices will give you an EIRP, which is useful. But silicon itself as a single device is a very poor performing RF device. But gallium nitride as a single device is exceptional. High mobility, high band gaps, so on and so forth. Okay. UCSB, and this is part of the propaganda. There's small little, give me a little, I'm the dean, so give me a little propaganda time. You can talk about at UCSB, the GaN device milestones have been myriad. So Steve and I actually worked to develop the first in 1996, the microwave power GaN HEMT demonstrated for the first time that actually RF power from GaN is a reality. Let me tip my hat to Asif Khan at the University of South Carolina, who was the person who invented the GaN HEMT. We did not invent it. We demonstrated for the first time that it was a microwave device. Then we demonstrated a kilovolt class HEMT. And this is, remember, in 1996, this demonstration led to the RF, the whole explosion of RF GaN. Okay, explosion as in market, not the devices didn't explode, hopefully. But then you have the kilovolt class AlGaN GaN HEMT, and this is basically and this is what has led to the whole market of power conversion in gallium nitride. Then we had, we developed this AlGaN aluminum nitride GaN HEMT, and I'll talk about this in later. And this is gives us the 2000 mobility that I talked about. This design is used in all HEMTs today. And then there is a discovery of polarization doping. This gave us the polarization doped graded HEMT, the PolFET, which you called it, and this is what is used by HRL today in their devices. And then we developed nitrogen polar GaN HEMTs in 2005, and the normally off P-type GaN HEMT. This device, this P-type GaN AlGaN aluminum nitride device, is the normally off device that is used in the majority of all compact phone chargers today. Okay, so this is the first demonstration of a normally off device. It's in every phone charger, not every, a vast majority. And then we basically did nitrogen polar GaN HEMTs, and then we will basically talk about how nitrogen polar GaN now is being funded thanks to Joshua Hawk when he was at Crane, the $200 million US program, of which 60 million has been let out. But nitrogen polar GaN is a 50% power added efficiency at 94 gigahertz device. Unheard of, unbelievable. Even I didn't believe it when I actually pitched it, but that's the job of a professor, to pitch stuff that even you don't believe. So this is Asif Khan's initial GaN crystal growth work in 1983 to 1990. Then the AlGaN GaN heterojunctions, that was in 1991. Ammonia growth, MBE growth of GaN was first done by ammonia. This was Hadis Morkoch and also Ted Moustakis. And then first GaN transistor in 1993, 94-ish timeframe was with, this is the Asif Khan device. And then in 1996, we did the first GaN RF power transistor. This is work done in collaboration with Steve. And there we, for the first time, showed that in the first attempt, gallium nitride devices could give 1.1 watts per millimeter, which was higher than the power density of gallium arsenide at that time. Of course, gallium arsenide has also improved with enhanced field plate technologies and so on and so forth. But what it said is, oh my God, this is the first time we did it. This was on Sapphire. This was by MOCVD, no passivation, and we got better than gallium arsenide. So rule number one in life is, if things are very hard to come by in the beginning, chances are it's not worth pursuing. But if things come a little easy in the beginning, but there's a lot of work to do, at least you have the motivation to do it. So next steps for a technology, and this I sound like somebody from DARPA. adoption of a new technology requires a major 10x improvement over the incumbent. Why? Because by the time you get good, the new technology gets good. The old technology is getting better every day, right? Look at silicon, right? What silicon, there were funerals planned for silicon in the 80s, and now they are planning funerals for the rest of us. So the issue is, unless you have that potential of being 10 times better, don't even go there, because the incumbent is going to beat you. Development also must be rapid, so that the return on investment can be realized quickly. If it takes very long to develop this shit, it's not going to be very exciting because the return on investment is bad. So what the most important thing that we had, but we had all this, we could hit bullet points 1 and 2, but the most critical issue that we had to solve was dispersion. What is dispersion? What looked good at DC, as you can see out here, we had very good current, an amp per millimeter, and so on and so forth. But when we pulse this device, and obviously every RF device is a pulsed device, you basically, at 200 nanoseconds, the current collapsed from 1 amp per millimeter to a fifth of that, and that's dispersion. And the reason for that primarily was charged surface traps. And the reason is, to solve Gauss's law and make sure that you satisfy Poisson's equations, you need an electron to balance the positive charges, but the electron need not be mobile. You need electrons to solve electrostatics correctly, but if the electron is immobile, those electrons don't give you current, and that's the problem. So when you basically charge the surface traps, everything is hunky-dory, but you get no current, and then these charges have to be released to give you current, and it takes a long time. So this is how we progressed in dispersion management. First, in the beginning, we had doped AlGaN. Okay, so our first devices that we grew in Steve's lab and in his homemade machine, the first devices that we grew were AlGaN GaN HEMTs, but we silicon doped the AlGaN. Okay, and that's the only way we could get devices to work in the beginning. Silicon doping of AlGaN. So from 1996 onwards, we got about 4 watts per millimeter, not bad in those days, with no passivation. Along came passivation, and then it jumped to 10 watts per millimeter. Then we introduced field plate technologies, and we went from 10 watts per millimeter to like 25 watts per millimeter. With multiple field plates, CREE in those days had 43 watts per millimeter. So now you have this hockey stick in technology development. That's always a good sign. In the beginning, you are basically in spontaneous emission. Nothing is coherent. You're just trying to find things. You're in kind of a search mode of a radar before you can actually focus. And once we started focusing, boom, you hit the threshold of the technology development, and that's what happens. Field plates are basically, you add capacitance to the system because voltage is only held by a capacitor. So if you want to have more voltage, you have to add more capacitance in the system. That's just Maxwell's equation. So you basically end up, you add a capacitor, you extend the depletion region, you relieve the electric field, you get more voltage. And this is the field plate concept, and it's very useful. And that's a standard fare today. We also did something I think this was very clever. Normally, AlGaN GaN HEMTs have a band diagram like this. You just have AlGaN and GaN, and electrons are here. And electrons actually see the aluminum gallium nitride material. The aluminum gallium nitride material is an alloy, and so it actually scatters the electron through the process of alloy scattering. We introduced a 1 nanometer thick aluminum nitride layer, thin aluminum nitride layer, which basically did 2 things. It separated the AlGaN from the GaN, but also, since aluminum nitride is polar, it has an inbuilt polarization dipole, you can actually, you lift the conduction band. So what you actually do is you can change the conduction band discontinuity, an effective conduction band discontinuity, which is this delta EC, which is what nature gives us. And then you add to it the polarization voltage of the aluminum nitride, you get a huge increase in effective delta EC without changing the two terminal materials, AlGaN and GaN. And you get a higher mobility simultaneously with higher charge. So all of a sudden, we went from 4 watts per millimeter to 8 watts per millimeter. And this basically was a big breakthrough in the gallium nitride technology. There was a lot of chatter in the early 2000s that GaN was not a millimeter wave technology. GaN was a sub 10 gigahertz technology, and that was because of this conversation around hot phonons and which limited the electron velocity in gallium nitride. Yeah, there was some truth to it, but it was not all, yeah, there was some truth to it, and emphasis on some, but it was irrelevant. So what ended up happening is we basically said, instead of kind of arguing against some theory, just make the damn devices. Thanks to Harry Dietrich at ONR and others, they gave us money to do this, and we showed that we could get 10 watts per millimeter at 40 gigahertz. And that kind of retired the naysayers who thought that gallium nitride, because of this hot phonon business, would be a 10 gigahertz technology. And in fact, at that time, there was some early work that also showed 2.4 watts per millimeter at 2.4 watts, sorry, total watts with multiple chips at HRL. And I'm talking about a long time ago. So this is exciting. So the material is good. It's not stuck at X-band. It's a technology for all frequencies. So that's very exciting. So that's the AlGaN GaN HEMT. So are there other promising device avenues for gallium polar gallium HEMTs? Yes, there is. And they're doing well. Okay, so here in two-dimensional electron gas, there's a graded three-dimensional electron gas channel that can be formed. This was work by Yulia Smorchkova, now at NG, and myself and DJ when he was a student at UCSB. This was an accidental discovery. This was not like planned. This was trying to do something like remove a conduction band barrier and eliminate a two-dimensional electron gas, and voila, we got a three-dimensional electron gas. And that started this whole field of polarization doping. It was a discovery, not an invention, but very exciting. And so then the pole FET, this is the minute you have a three-dimensional electron gas, it's a MESFET effectively without the scattering of the impurities that a MESFET needs. And you can actually change the doping profile by just changing the grading angle, the grading slope, sorry. So Siddharth Rajan, when he was a student here, made a HEMT and a parabolically graded pole FET, so you could change the GM curve at that time. All very exciting. Recent developments from HRL. HRL uses this, and Jong Moon has pioneered this at HRL and gotten great linearity from these devices. There has been multi-channel gallium nitride HEMTs. You see, gallium nitride HEMTs are good. Gallium polar gallium nitride HEMTs are good, but they have some issues with current. They don't have enough current and so on and so forth. More current is better, especially at millimeter waves. Because if you have very low current at millimeter waves and you have if you have low current and a high voltage, the only way to get power is to have high voltage. But if you have low current and high voltage, the load line is very shallow, i.e. the impedance is very high. And remember, the world is at 50 ohms next to you, right? That's the microstrip environment. And finally, vacuum is at 377 ohms. So the world that we live in is 50 ohms, and then an antenna has to talk to 377 ohms. That's it. So what you want to do is be as close to 50 as you can on chip. And having these very shallow load lines, which are highly high impedance is just a bad idea. So you really, as you go to higher and higher frequencies, you really want to make the current be higher and the voltage be lower so that the load line becomes more steep, closer to 50 ohms. So to do that on gallium polar, you need multiple channels. So here's a multiple channel device from Teledyne. This is work done by K. And he called this a bridge FET, where he could actually punch through these multiple channels and then basically squeeze them from the sides to control current, and got huge amounts of current, 3.7 amps per millimeter, which is awesome. And then there is the SLIC FET from Northrop Grumman on the East Coast, and Josephine Chang showed this data, where basically you again have very high current levels in these castellated superlattices, right? So that's to get more current and deliver more power at millimeter waves, especially. So the path we have chosen is at UCSB is one of nitrogen polar GaN. So the challenge of high power at W band today is the following. It's hard to get power at millimeter waves. It's hard to get power density at millimeter waves. It's hard to get power at millimeter waves. And here's an example at the device level, and I'm talking about 2022 now. This is a Jong Moon device, HRL device. As you can see how people have combining various devices to get power. Schellenberg, Brown, and then and this is basically work done at Raytheon. This is heroic work, and this thing actually put out multiple kilowatts. I can't remember how many kilowatts, but it's multiple kilowatts coming out of this device. And not device, this system, okay? But it had thousands of chips. So now the question is, yeah, you can do this. Power combining is always because power is a scalar. You don't need to, you can always take 2 or 3 or 4 and add the power together. But the power adding process is lossy, always lossy. So the more devices you have, the more power you get, but typically you'll get it at a reduced efficiency, or the loss is really a pain, because what happens is you end up with we have to remove all that heat from the system to keep the performance high and reliability high. So efficiency with power is the key, not only power. So we've talked about gallium polar GaN. Nitrogen polar GaN is just flipping it on its head, and it basically becomes an AlGaN back barrier with 2-dimensional electron gas on top. Paul Mackey at the ONR has funded me extensive, and now no longer at the ONR, but while he was there, funded us extensively on nitrogen polar technologies, as did DARPA under the DREAMS program, Tom Keisha. So then the nitrogen polar device has the following. It has AlGaN at the back, GaN on the top. And then you have these ohmic contacts, N plus GaN ohmics, and they basically connect to this 2-dimensional electron gas. Okay, so this is very nice because you're making a contact to a low band gap material, easy to make contacts, and you have a back barrier as well. And I'll come to the advantages in a minute. I'll explain it in a minute, but let me tell you what the problem was. So growing nitrogen polar GaN by MOCVD is not easy because the surface mobility of the gallium atoms is low when the surface is nitrogen polar, because the nitrogen atom tends to stick to the gallium and prevent it from finding its natural site, and you get halox. And this basically, Stasia Keller actually ended up doing a seminal study where she looked at growing nitrogen polar on miscut substrates, and we ended up with smooth materials. And now we do 4 degrees miscut to give us process latitude. 4 degrees miscut materials. With that, what ends up happening is you end up with a very smooth surface, but you still have these ionized surface states, these surface states that give you dispersion. But the beauty about nitrogen polar GaN is you have a different way of solving the problem. And what is that? You can have a two-dimensional electron gas, but then you can grow gallium nitride again on top. The beauty about put gallium nitride on top is, let me see if, yeah. It's not showing up well here, but it's okay. Gallium nitride on top, the polarization of the gallium nitride on top is such that when you grow this gallium nitride on top, it actually enhances the gallium nitride 2 deg below. That is, if I did, because the polarization is such that the surface potential here drops as the more I grow. And so when I put GaN, two good things happen. I get more charge in the channel, which means my Ron decreases. And I move the surface away from the 2 deg, so my dispersion decreases. So a GaN cap actually reduces the resistance of the channel and reduces dispersion simultaneously. We use silicon nitride at the moment as a insulator for the GaN, but there is new work happening at UCLA with the Lehigh, where they're doing hafnium silicon dioxide, and we'll look forward to that later. The band diagram didn't come up very well, but it's okay. All I want to say is that when you have more charge in the channel, you don't have a current choke. And so you can actually, when the resistance of the channel drops, as I pump more and more current in the channel, the resistance of the channel doesn't rise. There's enough current, there is enough charge in the channel to carry the current without saturating the mobility. So the resistance remains low. Very important. Of course, you can have field plates on top. So here is a typical device will be a gallium nitride channel like this. And this gallium nitride channel followed by the gallium nitride cap gives me a very high threshold voltage. What do I mean by a threshold voltage? The surface has been moved away. So if an electron gets on the surface, the electron on the surface cannot deplete the electron in the channel easily because the capacitance has been decreased. So the threshold voltage of the region in the cap is much higher than the region underneath. And that's basically the threshold voltage of the access region. We typically design around 20 volts. And this is around 6 volts. So between 6 and 20 volts, the surface doesn't even play a role. And after that, the silicon nitride passivation kicks in and helps the dispersion to remain low. So we have a 2-level dispersion control. One is at the epitaxial layer, which is the GaN, and a silicon nitride on top. So we get terrific dispersion, less than 10% dispersion through 16 volts in the device. Very good current and a very good looking FET. So this diagram actually tells you that there is, you see, in this case, the band diagram showed up well. So when I put gallium nitride on the surface, you can see that the electric field in the channel gets reduced because the band, when I put gallium nitride on the top, it pulls the bands down. So it adds charge here and a little charge on the top. This device is nearly perfect in the sense, not in an absolute sense, but as a FET, in the sense that the same device, this is Brian Romanchik's work, the same device can put out power, the same device puts up the same watts per millimeter independent of frequency. At 10 gigahertz, it puts out 8 watts per millimeter. At 94 gigahertz, the same device puts out 10 watts per millimeter. And this is important to recognize because this is the first demonstration of a device that actually puts out the same watts per millimeter independent of frequency. Watts per millimeter should never be a function of frequency. Watts is a function of frequency, of course, because of all the impedance matching and all you have to do, but not watts per millimeter. So nitrogen polar GaN actually turns out to be quite spectacular. Here's an example of gallium polar GaN. It hits a wall in watts per millimeter and efficiency. This is where it is. But nitrogen polar GaN on silicon carbide and on sapphire is spectacular. So you can see that you can get at 5 watts per millimeter, you can get more than 40% power added efficiency. And in fact, at 3.7 watts per millimeter, this is a little old, this slide, I'm sorry, I didn't update it. But at 3.7 watts per millimeter, now we have 52% power added efficiency. So you can see how nitrogen polar GaN just broke through the wall that was holding GaN. Watts per millimeter is nice, but what you need is watts. So for that, you have to have an air bridge structure like this. Axel and Henry Collins worked together on this. And you can see what we did was we did air bridges over multiple fingers, like every self-respecting MMIC designer does. But the only difference that we did was we also used the air bridges to do impedance matching close to the device. So this is a pre-matched device, not fully matched, pre-matched, so that the load pull system could match the device better. So this is what we have done. And we did a lot of modeling, both by COMSOL to give you capacitances right, and by HFSS to give you inductances right. We did all this because you have to do it right to match, to create the right matching circuit. And we did a big study, but the most important thing that I want to tell you is after doing these models and actually implementing it into the device, what we found out was that what we modeled was that the air capacitance of the air bridge would be about 15 femtofarads per millimeter. What we got was 17 femtofarads per millimeter. And what we modeled by HFSS was 3.2 picohenries, and we got exactly 3.2 picohenries when we built the device. So the models were correct, the implementation was correct. And we ended up getting excellent devices. We got single device, one device at 94 gigahertz, giving you 712 milliwatts with 32% power added efficiency, 7 dB of linear gain. This is really, truly exceptional. When we try to get even more power by instead of having a 4 by 25 micron device, this, by the way, was a 4 by 25 micron device. When we did a 4 by 37.5 micron device, unfortunately, we couldn't match the device with a passive load pull system. So thanks again to Paul Mackey, who gave us a DUREP to develop an active load pull system. An active load pull system, basically, as the name suggests, is not based on only tuners, but it actually puts in power both at the input and the output, and then basically extracts the net impedances on either side and constructs the load pull diagram on the Smith chart that way. Using the active load pull system, we could match the 37.5 micron device, and we got a watt at 94 gigahertz from one device. Again, if you look at the total power here, you can see gallium polar devices are here in total power. Nitrogen polar devices have again broken out of the wall in total power. And it's always important to make sure that we verify this, that is this what we measure, is it true? And we do this by doing a CRIPS analysis. We do this routinely. Every time we measure something, we do a CRIPS analysis. That is, we want to make sure that the load line that we are actually measuring on load pull is what the load line of the device should be if it's well behaved. And we always do this. This is the measurement. This is the theoretical verification. And you can see that we are very close, and hence we believe our measurements. So with that, what I'd like to do is conclude the technical portion of the talk and then share with you a small video about what the gallium nitride effort at UCSB has been. And this is a video which was produced with the cooperation of Steve, and Jim Speck, Shuji Nakamura, and myself. And it's just for 5 minutes, so I hope you enjoy it.
Light-emitting diodes, or LEDs, illuminate Henley Gate, the iconic east entrance to UC Santa Barbara. The blue hue spotlights the pioneering and collaborative research of gallium nitride, commonly referred to as GaN, that has occurred on this campus for decades.
No other university, in my opinion, in the United States has impacted gallium nitride like we have.
It's a bold statement, but one that Mishra and the other co-founders of the Solid State Lighting and Energy Electronics Center, Stephen Denbars, James Speck, and Nobel laureate Shuji Nakamura, who invented the blue LED, support with facts, starting with the cumulative impact of their work to improve the efficiency and brightness of LEDs.
A lot of people forget when Shuji came here in the year 2000, LEDs were only about 20 lumens per watt, which is about 5% efficient. So at UCSB, we increased that efficiency, over tenfold to, 72% efficiency, 200 lumens per watt. So that's 10 times brighter, 10 times more efficient.
Their work thrust LEDs into everyday life and lighting everything from cell phones and TVs to cinema displays and automobiles. Recently, they've also emerged as world experts in micro LEDs.
Particularly the sphere is really mind-blowing to see that, the largest display in the world is made with LEDs. And the brightness of those LEDs were improvements made here at UCSB. And that's a fun thing about research is you can never imagine where it's going to end up.
The Department of Energy estimates that by 2030, LED lighting will save $250 billion annually in the U.S. alone. And by 2035, the annual energy savings in the U.S. will equal the output of more than 91,000 megawatt power plants.
Because of Suji's pioneering work and a lot of the work we did on the materials at UCSB, I think every GaN LED has some DNA going back to UCSB in it, and I think that's great.
UCSB's GaN impact reaches far beyond lighting and displays. Advancements made here also revolutionized the electronics and communications industries when they were applied to high electron mobility transistors, or HEMTs, establishing UCSB as pioneers of power electronics.
The HEMT application towards microwaves, which actually made it what it is today, happened here in 1996. And we basically did most of the work on gallium polar HEMTs. And then for the last 15 years, developed a whole new field of nitrogen polar HEMTs, which has completely changed the game when it comes to the next generation of wireless communications.
Today, game-changing discoveries made at UCSB are powering radar, data centers, 5G base stations, phone and laptop chargers, and electric vehicles.
You look at 5G base stations today, all the new rollouts are gallium nitride. So when you talk on the phone, it's UCSB's fingerprints are all over it.
All of the essential work in GaN transistors started at UCSB, and that field is going through its similar explosive growth right now that LEDs have already gone through.
These centers' numbers speak for themselves. They've received $76 million from industry members, produced more than 1,400 publications that have been cited nearly 65,000 times, amassed 377 active patents and applications, trained more than 150 Ph.D. students, nearly 20 of whom are faculty, and they launched nearly 10 successful startups.
Umesh and Jim and Steve, they are so smart and hard work. We developed all kinds of gallium devices all working together. So it's amazing. We did start it with the idea that we wanted it to be a team effort, and because we always felt that that's one of the things UCSB does better than just about any other U.S. university, is we do really good collaborative research.
Considering the discoveries, citations, students, and influential technologies, UCSB is an engine of GaN innovations for social impact.
All this doesn't happen by wishing. It requires sustained effort over time. UCSB has done that. We have stayed true to our North Star, And results proven.
Oh, shucks. Hang on. Now I don't know how to get out of here. Hang on. So thank you for listening into that video. I know it's a little bit of a marketing thing, but I just want to summarize everything that I've spoken today, and hope that it's been of interest. Nitrogen polar GaN has turned GaN design on its head, literally. Gallium polar continues to improve, though. Like I said, don't ever knock something that's working. It always improves. And the doped algan hemps are now, there's a resurgence, and scandium aluminum nitride barrier hemps, graded channel hemps. Nitrogen polar GaN remains ahead at millimeter waves, but there's a lot of action going on, and it's all good. Devices on N polar grown MB substrates have show great promise, not part of this talk, and also thermal management. And the N polar GaN substrates work done by Lehigh at UCLA, and thermal management done by Shravanti at Stanford are all going to help all these technologies keeping on moving forward. So I'm actually very excited about the future, and I hope we all kind of enjoy the ride. Thank you very much.
Thank you very much, Umesh. We can take questions. While we're queuing up questions, I want to congratulate Umesh on the great talk and the great impact that GaN has made, and the contributions of UCSB to that impact. And also congratulations for getting the sound to work on that video in today's presentation. That worked out very nicely.
Thanks.
And then lastly, I'll say that my wife does lighting design for community theater, and LEDs have revolutionized that world too. So we'll have to get that added to the next version of your video.
Perfect.
And with that said, I see Roger's hand up.
Hi, this is Roger Lake at UCR. Great talk. Thank you. Can you hear me?
Yes, we can. Thank you.
Great. Thank you. I have a very mundane question about contact resistance.
Yes.
So is that something that's going to limit the ultimate frequency at which GaN can operate? I agree it's great for power, but in terms of frequency, it seems like contact resistance is something as mundane as that could eventually be a limitation.
That's actually a very good question, Roger, and thank you for asking it. The interesting thing is this is where God actually helps us. Okay, the greater power. If you look at gallium nitride, the conduction band of gallium nitride is such that if you look at normal metals, aluminum, titanium, all these metals, actually the work function of it is such that it lines up very close to the conduction band of gallium nitride. And if I grade gallium nitride to indium gallium nitride, the conduction band actually goes below that of the metal. So what ends up happening is connecting to gallium nitride conduction band turns out to be as easy as connecting it to indium gallium arsenide. We have got now contact resistances of 20.027 ohm millimeter to gallium nitride. The problem with gallium nitride is contacting the valence band, because the band gap is such that the valence band is far away from metals, but the conduction band is very close. So we are very lucky that way, that the lineups are such.
Thank you.
Okay.
Hi, Umesh.
Yes.
This is John HRL.
Hey, John, how are you?
That's very good presentation. I love that. Looks like the M-polar, the very good performance and W band came out in this sapphire substrate, right?
Yes, sir. We have both silicon carbide and sapphire, but it's our high efficiency records at the moment are on sapphire. Yeah.
So do we need to worry about the thermal thing on the Sapphire? Looks like we do not have to worry about thermal interface Sapphire.
That's a very good question. I think it depends. So if you are trying to get a gajillion watts out of it, right, then I think Sapphire is going to hurt you, right? So the reason. So there are two reasons. One is if you get a very good. I mean, I'll say something relatively kind of, and apologize for it being so stupid, but I'll say it anyway. The way to actually don't have a thermal problem is to not generate the heat, right? So having a very high efficiency device is the best way to actually address the problem. So having a 25% device power added efficiency versus a 52% power added efficiency device is a huge deal in the amount of power you generate. The second is, if the devices are small, if you're generating like a watt of power or half a watt of power, then you don't need I think silicon carbide is not particularly necessary. But when you get to like 2, 3, 4, 5, 10 watts of power, and you end up generating a huge amount of power in the device, then Jong, I think we can't run away from it. So I think it depends, like I said. So, but we are pursuing Sapphire because in many applications, it does really quite well. Yeah.
Thank you.
Thank you.
Hand up from Tim. I'm guessing that's Tim Lee. Only needs
Yeah,
one
hi.
name.
Yeah, hi there.
Hi, Tim.
Yeah, Umesh. Hi, how are you? Have you gotten any N-polar mimic results on thin wafer and with through substrate vias to lower the source inductance?
We have not got nitrogen polar circuits with in a microstrip environment as yet. We are working on it, and but we have got nitrogen polar circuits on a coplanar waveguide without through surface vias, but not because for two reasons. One is our Sapphire devices, we can't make a through surface, a through substrate via easily, but on the silicon carbide we can, but we don't have that technology. So we are actually so we have stuck with coplanar. But it's a good question, Tim, but we are doing it right now as we speak.
Okay, yeah, thank you. Yeah, thank you very much.
Thank you.
Priya has a hand up.
Sripriya?
Yes, hi. Thanks
Hi.
for a great talk. You know, I think it's really exciting what gallium nitride has done for basically the LED world, as Steve was saying, as well as like all the progress made at UCSB. So my question was, you know, if you were to pick a future application where gallium nitride can have a similar impact, like, you know, kind of changing the paradigm, what would you say, or where should we be looking for that?
Actually, that's a very hard question to answer because I don't know. Do you mean like greenfield, like something that is where you can start from scratch and go somewhere, right? Is that what you were saying? Or so, because the way I look at it is we have barely begun working on what gallium nitride can do in say nitrogen polar GaN. Like, you know, Tim asked a very simple question, which I had the answer to, which was I haven't done it, right? So I think that greenfield, we can have a separate conversation. I have wild thoughts about that. And I don't like to share that in public because they're just totally crazy. But I believe that gallium nitride can solve many problems in not only in the microwave and millimeter wave domain. But it's a little of a long shot. But in the microwave and millimeter wave domain, I think we have just begun. And I think one of the things that is important to do is and Steve knows this very well, is to democratize this process more. That means get more people involved in actually moving this technology forward, not only at the technology end, but the application end, the circuit end, And I think that we have not even begun doing that. So we have to actually arrange an ecosystem, and Steve is aware of that. He knows what I'm talking about. But it's like we have to arrange it such that more people can get involved in it. And then, as Steve Denbar said, you don't know where it'll end. If more people get involved, the future will take care of itself. That's what yeah.
Well, thank you so much for that, Umesh. I do visit the UCSB campus, and I'm hoping to get out to USC. Traveling next week, I can't attend the event, but when I come by next time, work with Dee
Give
and
me a
Watson.
holler. Yeah, give me a holler. I got coffee in my office, nothing more.
Okay, well, thank you.
Thanks.
Thank you, and I'll take that as a plug for Moses 2.0. Let's see, you has a hand up.
Prof. Mishra, yeah, thanks a lot for the great talk. Yeah, and actually, Yulia from your group before she also demonstrated a very excellent work in the Alumnus hand work.
Exactly. I mean, I that's why I mentioned her. Yeah. So.
Yeah. Actually, my question is about the comparison of deep recessed GaN HAMT in a gallium polar versus the N polar, because your team had both experience in these two structures. So what do you think is the reason preventing deep recessed gallium polar GaN HAMT reaching the same high level of output power, like the excellent performance compared to nitrogen polar?
That's a very good question. Again, I think that so Likun Shan and Rongbing Chu, and even I think Ipe may have also done this, but I can't remember. I have so many, it's like when you have many children, you forget their birthdays and their names, and I forgot. Anyway, but I hope I have not forgotten any of my students who've done this work, but those three I know. So what we found, there's a fundamental issue which can be overcome by technology. The fundamental issue is when you grow GaN on top of AlGaN, you deplete the two-dimensional electron gas underneath it. So instead of adding to the 2-deg, you deplete it. Okay, and so what you have to then do is you have to counter-dope it, correct? When you start counter-doping AlGaN with all kinds of things, what we found is typically that AlGaN, the breakdown fields in AlGaN and all these things and tend to degrade, And so the material nitrogen polar GaN, because it can, the nice thing about gallium polar GaN is, nice thing about nitrogen polar GaN is all the doping is underneath, right? So we can dope the AlGaN to get the charge. You add GaN on top, you get more charge. So under the gate, you don't have to actually dope and all this. But in gallium polar, you have to dope excessively. Now, K is doing that. We'll see where he goes with it finally. But he's doing it without putting GaN on top. If he puts GaN on top, which we did before, you have to add it. We have to add a lot more silicon to take care of the depletion. I'll tell you basically what ends up happening is if you put GaN on top of AlGaN and you keep growing GaN for about 27% AlGaN, the amount of charge that's left behind is 4E12. So you start at say 8012, you're down to 4E12. You've got to add 4E12 more charge. And you have to do it in a very small doping region to keep the aspect ratio right.
Yeah, the window
just gets hard. Yeah, it paints you into a corner. That's all.
Yeah, okay, thank you.
And Umesh, if you don't mind taking one more question, I have an anonymous question from the chat window. Okay. The question in the Q&A window is, given the ban on gallium export from China, do you expect any disruption in the future?
Yeah, that's, I don't know the answer to that question. That's actually a very valid question. People are worried about it.
Yeah.
So I think that I think it's not yeah, there might be some disruption. The thing about gallium polar GaN, I think is a bigger problem for materials that where you have to grow thick epi, right? So I think like vertical, I mean, even LEDs, to make an LED, you typically grow on sapphire, you grow 8 microns of GaN before you get to the LED. We grow less GaN, right? And so we consume very little GaN in the RF domain. And so will it hurt us? Could have hurt us, but yeah, I don't know the answer to that. But at least we can get away with growing 1.5 microns of stuff and get good performance as opposed to needing to grow multi-microns.
Okay, thank you. And thank you very much for the seminar and taking the questions. That was great. As we wrap up, I'll just point to the screen here, registering for future seminars. And if Amy could advance to the last slide, just a quick preview of some of the talks coming up that will have a high bar to live up to after Umesh here. But next week, we are excited to have Azita Imami from Caltech speaking. The week after that, Mike Chen from USC, Mark Redwell back to UCSB. The week after that, and Shia Feynman from UCSD is coming up after that. Thank you very much, everybody.
Thank you. Bye-bye.
Bye.